Manches morning, everyone. I hope you are doing well despite the inclement weather that we are expecting. If it's not inclement, then you are viewing this video is as a preparation for one. Okay. Um, there might have been some queries on the Springboard 0.3, which is review on atomic models. So in your module, you can see it here, the link. And as it turns out, there are actually two versions of the simulation. Okay, and then this is a new one, the browser compatible version, which runs without downloading. However, I'd like to recommend that we download the Java version, which is way uh, better in terms of performance, and it has a functional spectrometer. So all you needed to do was to click this button here, Java version, and then I actually have something downloaded in my laptop already. Okay, and so let's get to open that one. Maybe keep this first. And then there might be some prompts or notification asking for your permission, especially for Mac users to run the simulation. Okay, so you already know more or less how to manipulate this one. We turn on the um, gun, the light gun, and you see that a white light is being depicted as a uh, collection of different colors, the colors making up the rainbow. Okay, remember that in the electromagnetic spectrum, okay, it's a wide spectrum, and then part of it is visible light, and so this is what is being used in the simulation. Now remember that visible light is composed of photons of different colors. And why do they have different colors? That's because they have different wavelengths. Okay, so the longer the wavelength, okay, the lesser the energy. The shorter the wavelength, the higher the energy. So if you remember, red has the longest wavelength, violet has the shortest wavelength. Now, if you try to run spectrometer as it is stated in number 4, procedure number 4. Okay, let me just show it here. Okay, you were asked to use monochromatic light. When you say monochromatic, that means only one color. Now, you are asked to start with UV, right? So if you are going to start with UV here, then you might have noticed that most of the measured values are registering along the UV area. Okay, but there are some very rarely that go to the blue area or to the wavelength corresponding to the blue or violet colors. So this is what's expected out of the simulation, and I'm afraid the Chrome based or the web-based simulation really takes time to show this. Okay. Now, if you downloaded your simulation already, the Java version, and it's still not showing, you can always restart the simulation because this one takes a very long time also, a number of minutes, really. So what we are actually studying here is what could have made UV light change its wavelength, okay? Because there is a change in wavelength, there is a change in color for some of those photons, okay? And what happens to them? Okay, what happens to their energy? What happens to their wavelength? What could have happened inside the box of hydrogen atoms? Okay, so that's the secret. Now remember that you are actually what we are seeing here right now is what happens in an actual experiment. So this is what is empirically observed. Okay, and you know that different models have been depicted, models of atoms have been developed. Okay, so you take note of what actually happened in the experiment, compare it to the predictions by the billiard ball model, by the plum pudding model. Okay, I'm pretty sure you are familiar with all of these. So what we are doing now is enriching that understanding. Now, what could have happened to the photons that interacted with the box of hydrogen atoms, or with the hydrogen atoms in this mystery box? Okay, and then if I were to view the prediction, if I were to view how it is here, then what makes them different, and which gives me the more accurate version. Okay, sometimes you're also asked to go through the different models and you look at. Okay, so this is the Bohr planetary model, wherein if your electron, the blue dot, interacts with a photon, it changes energy level. Okay, if you remember, these are your energy levels. These are your orbits. These are your n in your quantum numbers. So if the electron is hit by a photon with a certain energy, it transfers a higher energy level up, but it cannot stay there forever. Okay, it goes back to the lower energy levels, and in doing so, it registers different photons, or it emits different photons of different wavelengths. All right, and so if you remember atomic spectra experiment, the principle behind fireworks, this could be a very good explanation. All right, so I leave it up to you to answer the next few exercises. Make some changes in your answers. That is very much fine. I'll be keeping the page open. Okay, if you have any more questions after this video, then just feel free to hit me up. Okay, I'll be more than willing to answer. All right. So my goal for you here is to trace the development of the atomic models from the billiard ball down to the Schrödinger model, okay, or the electron cloud model of the atom, and see how the understanding of the atom evolved in the process. What evidences were presented, what experiments were done, okay, to verify or to refute the atomic model concept, the existing atomic model concept. Okay, so that's it. Just take note of what's happening in the spectrometer. Okay, why are there different colors if we are using UV light? Okay, why have there been photons emitted that have lesser energy and longer wavelengths? Oh, you see a red being registered. Okay, the red color is way less energetic than the UV. So what happened to that energy? He figured it out. Okay, so thank you very much, and yeah, you may enjoy the next few lectures.